This is some start time feedback to help you out improving Quantitative Task 2, determining the molar mass of an acid from May 2012. So if we have a look at the first part of the quantitative task, this isn't something you're going to be asked to do in your exams, but it is still skills development. You had to take some readings and some measurements. Now the marks in this section here come from number 1, recording the mass of the bottle and the mass of the empty bottle correctly, and also then calculating the mass of the acid that you've used. Most importantly, you need to make sure that all masses are recorded correctly and to a consistent number of decimal places. So in this case it needs to be 2 decimal places, as it was a 2 decimal place balance that we used. When we come onto the table, there's quite a lot of marks available here. The marks in this case come from consistency, so obtaining 2 titers that are within 0.2 of each other, 1 mark for 0.2, and if they're within 0.1 of each other, then that's 2 marks. You then have a number of marks, 5 marks there for recording. In order to get all of the marks, what you need to make sure of are the following points. The initial and the final readings and the subtractions are all correct. That you've used 2 decimal places for all readings, even for the 0 reading of 0.00, and the last digit for burette readings is always a 0 or a 5. Finally, the mean is calculated using only the closest titers, and it's calculated to 1 decimal place, as that is what is asked for in the table just here. Most students forget to do that. When you're looking at the titers, you've got all of your titers at the bottom here, so your calculated differences. And in this example, the student would use the 2 titers that are closest. So that would be this one, 20.65 and 21.00. We would exclude the other 2 when calculating our average. The other 3 marks, again, you can't be assessed on this in your examination, but it is important for you to know. They came from accuracy. And there are 3 marks based on how close you were in your results to the teacher, so how close you were to my results. And the better you are with your skills, the more accurate you become, the more progress you'll be able to make in terms of your examination questions. For part 2, which is the analysis, we start off by having a balanced symbol equation at the top, and that indicates the stoichiometry. The first question is asking us to calculate the amount in moles of sodium hydroxide used in the titrations, and you can see that this student here has got it correct with 2.5 times 10 to the minus 3. It doesn't matter whether you record this in standard form or non-standard form, and the way that we get that answer is by taking our number of moles of NaOH, which is equal to our volume, 25 centimetres cubed, over 1,000 to convert it into decimeters cubed, and multiply it by the concentration of 0.1. Now both of these pieces of information are given to you in the question, or at least in the method. You must make sure that you use the right volume of sodium hydroxide, which is 25 centimetres cubed. Following that, in question B, it says, using the equation above, so you do need to refer to the equation, calculate the amount in moles of H3X in your mean titer. It's telling you here it's in your mean titer. So the amount that you use from the burette, that's the amount of moles that you're calculating. Now because the stoichiometry is 3 to 1, what we see is that once we've calculated our number of moles of sodium hydroxide, the amount of moles of acid is actually 1/3 of the amount of moles that we had up here. So if we take this and divide it by 3, then we end up with our answer that we've got just here. Common errors here are that instead of dividing by 3, for some reason students multiply by 3. So it's important that you get your stoichiometry the right way round. Now in order to answer the next question, it's important that you recognise that this is the number of moles that are present in the mean titer, so i.e. the volume that you used from the burette. In the example that this student used, it was 20.6. So from this student's table you can see there that the mean titer was 20.6. The next question asks to calculate the moles in the 250 centimetres cubed that you prepared. So, if we know that we've got this many moles in our mean titer, and we know that our mean titer is 20.6, it's not as simple as scaling up like we have done in previous examples by a factor of 10, because 20.6 multiplied by 10 does not give us 250. So the easiest way to do this is to take your number of moles that you've got in your mean titer, divide the number of moles by the mean titer, which gives you the number of moles per centimetre cubed, and then to scale up by whatever factor it is that you're looking at, so 250 in this case. If we do that, this is the number of moles that this student's example would give, but your value will depend on your volume that you had in your titration. The next question, question D, which is over the side there, asks us to calculate the molar mass in grams per mole and to give your answer to the nearest whole number. In order to calculate a molar mass, we have to rearrange our standard equation N equals M over M. Molar mass is equal to mass divided by number of moles. You need to think where you get these two pieces of information from. The first part, the mass you used in the practical, that was the actual mass from the balance readings that you took. That means that it's the mass that you're going to find in the table at the top of page 3. You then have to divide it by the number of moles. The number of moles is what you calculated as your answer in C. So for this student's example, we've got 2 divided by 0.0100782. Now again, your mass and moles will differ, but important things to consider here are that you haven't rounded this number. So when you calculated it up here and you wrote it out, even if you rounded it on the paper, when you go on to do subsequent calculations, you always use a full calculator value, otherwise you end up with too many errors. This gives us a value of 198 for this student's results. The last question, question E, is actually not based on the information that we've extracted. It's kind of a separate thing altogether. You can see that we've got 210 as being the molar mass of our acid attached to a number of moles of water, but we don't know how many moles. Use this information and the structure of the anhydrous, so anhydrous means without water, acid, to calculate the value of N. The way that we would approach this question is to consider if the acid bonded to the water has a mass of 210, we know that H3X has a molar mass of 192, and the reason that we know this is we added up all of the masses from the structure in the diagram. So we looked at this, we counted up all the carbons, hydrogens and oxygens, and then we figured out what the mass of that was, and it was 192. If we take 192 away from our total mass of 210, we're left with 18. 18 therefore represents the number of the mass of the number of moles of water that we've got. If we rearrange the equation, so the number of moles of water has a mass of 18. If we do the number of moles, it's equal to 18 divided by water, i.e. divided by the mass of water, we end up with a value of 1. So in this case, we can be sure that when this substance is associated with water in a water of crystallization, the number of molecules of water that it associates to would be 1.